Our next speaker is Waddy Taylor. His title is Elliptic and Genus 1 Fibration Structure of Known Calabi Yau threefolds.
Great. Okay, I'd like to join the other speakers in thanking the organizers for putting together this nice meeting. I'm enjoying it very much, for a lot of very nice talks. And after last week at String Pheno at CERN, it's really nice to be in a place where one's not hot all the time. Okay, so I'm going to talk today about some aspects of Calabi Yau threefolds, in particular the elliptic fibration structure of many or most elliptic Calabi Yau threefolds. Much of this is based on a series of papers with my student Yuqian Huang, the most recent of which will appear hopefully in the next few weeks. And then there's a number of things I'll touch on related to ongoing work with a variety of collaborators, many of whom are here in the audience. So I guess 4 years ago at String Math, I talked a little bit about some related things, although I think we've come a long way since then, so I have a more, I think, complete and compelling story to tell you today. So just to briefly outline, I'll start by just a little bit of introduction about Calabi Yau's elliptic fibrations, what we mean by those things, and then I'll focus on reflexive 4D polytopes, and I'll talk a bit about the fibration structure of those polytopes. And then we'll go to triangulations, which are related to the toric varieties that live as hypersurfaces in those polytopes. And then at the end, I'll say some things about mirror symmetry in the context of toric constructions. So Calabi Yau manifolds have, of course, been used for decades in superstring compactifications. They have a couple of features that make them very valuable for string theory and for trying to understand how string theory gives quantum gravity in 4 dimensions and also in 6 dimensions. Because they admit a Ricci flat metric, they solve the Einstein equations, and because they have Kähler structure, they have a complex structure that's compatible with supersymmetry, so we can get supersymmetric compactifications, giving us a supergravity theory. Mathematically, they're characterized by the fact that the canonical class vanishes up to torsion. And these, again, have been studied for a long time, used in compactifications, but still there's an open question, which is, are there a finite number of topological types of Calabi Yau threefolds? And I guess Yau conjectured maybe 40 years ago that there were in fact a finite number, and I think what I'll say today is at least some evidence that that conclusion is correct. So a lot of large classes of Calabi Yau threefolds have been constructed. One of the first large classes was the so-called complete intersection Calabi Yaus. There's about 8,000 of those constructed by Candelas and company many years ago. A larger class, there's a little typo there. It says 473.8. There's not a 0.8 of a Calabi Yau. That's actually 473.8 million. I've dropped the capital M that should go in there. Sorry. And I could have fit it in that line. Okay. And then there are generalized CCs, which have been studied by the Virginia Tech group in recent years, and then elliptic Calabi Yau threefolds. And much of this talk will focus on these two sets, the toric hypersurface Calabi Yaus with 473.8 million Calabi Yau, reflexive 4D polytopes, and elliptic Calabi Yaus, which will focus on the connection between those two things. So let me just say a little bit about elliptic and genus 1 fibered Calabi Yaus. So if we have a projection from the Calabi Yau to a base, basically we can have an elliptic or genus 1 fibered Calabi Yau if there's such a projection map where the preimage of the generic point is a torus, and it's called elliptic if there's a global section, otherwise it'll be genus 1. So in general, an elliptic Calabi Yau can be described by a Weierstrass model, a simple equation of this form where F and G are sections of certain line bundles over the base. And elliptic Calabi Yau threefolds have a lot of additional structure, which makes them much more manageable mathematically. They're also important in physics because they're useful in the construction of 6-dimensional gravity theories. We use a 4-dimensional elliptic Calabi Yau for a 4-dimensional theory. So just a comment on the structure of this talk. Most of what I'm going to say today is more mathematical in the sense that it relates to the mathematical structure of Calabi Yaus, but the motivation is largely coming from physics. The reason we want to understand, or the reason I want to understand elliptic Calabi Yau manifolds is for the purpose of understanding F-theory, and the methodology that I'll use in the talk is sort of a physicist-style combination of experiment, by which in this case I mean direct computation, and more theoretical approaches. So recently, there has been an accumulating amount of evidence that, in fact, most known Calabi Yau threefolds have some elliptic or genus 1 structure. And just to be careful, what I mean by that is that most known Calabi Yau threefolds are birationally equivalent to an elliptic or genus 1 fibrid Calabi Yau threefold. So using a combination of physical and mathematical methods, we can actually get a very nice and systematic global picture of the set of elliptic Calabi Yau threefolds. So before I talk about how the set of Calabi Yau threefolds that are elliptic fits into the broader set of known Calabi Yau threefolds, I want to talk a little bit about our global picture of the set of elliptic Calabi Yau threefolds. So how would we classify or characterize all the elliptic Calabi Yau threefolds? So there's a theorem by Mark Gross which says that there are a finite number of topological types of elliptic Calabi Yau threefolds. And again, using some intuition from F-theory and some mathematics, we can systematically construct these elliptic Calabi Yau threefolds. Antonelli Grassi showed that the base supporting the elliptic fibration must either be a Hirzebruch surface Fm with m less than or equal to 12, P2, or the Enriquez surface. The Enriquez surface is kind of boring because the canonical class has only got torsion, it's trivial up to torsion, so it doesn't give us much interesting, so we'll focus on the others. Or blow-ups of those spaces. So we can take F4, for instance, and blow it up iteratively and get more and more complicated bases. But there's an upper bound to how complicated those can get. So one way of thinking about this is that if we take one of those minimal model bases, the Hirzebruchs or P2, we can think of the blow-up as just tuning a 4-6 singularity in the Weierstrass model. And if we look at, therefore, as a specialized Weierstrass model, and if we think about the set of all possible Weierstrass models over a particular base, there are a finite number of strata, meaning different algebraic structures that give rise to different elliptically fibrid things. So that's another, essentially gives rise to an algorithm for constructing all the elliptic Calabi Yau threefolds. To spell that out a little bit more explicitly, we can start by constructing all the bases, the B2s, that will support elliptic Calabi Yau threefolds by essentially just iteratively blowing up these minimal model bases. And that we've done at least at large H21. Things get a little more complicated when you go down. And then over a given base, we can tune the Weierstrass model to get various kinds of singularity structures, which in F-theory are associated with gauge groups, matter, and structure like that. So we can, for instance, start by tuning codimension 1 singularities, which were classified by Kodaira. They're associated with certain Dynkin diagrams, which in the F-theory language give us gauge groups. This is mostly well understood. It's a bit more complicated when we talk about U1s, which have to do with the Mordell-Weil rank of the set of rational sections, the group of rational sections. It's understood when you have 2 U1s, but not more. Discrete gauge groups with multi-sections and genus 1 fibrations, genus 1 fibrations are a little less well understood. And codimension 2 singularities, which give rise to matter in the F-theory language. For generic matter charged under non-abelian gauge groups, we understand that. There are certain kinds of exotic matter, and when we get complicated products, that's not as well understood. Okay, so just to sort of run through this in a little more detail, how do we systematically construct the bases? Well, we can start with those Hirzebruchs and P2. In the toric geometry language, it's totally straightforward to just combinatorially blow up as much as you can until you get stuck. You get stuck because you can't have a curve of self-intersection minus 13 or below. That would force a codimension 1, 4, 6 point in the Kodaira classification, which is not allowed. So we did that with Dave Morrison. There's 61,000 toric bases. The generic elliptic fibrations over those toric bases give the blue points. The gray points here are the Hodge numbers of the hypersurface in the toric hypersurface Calabi Yaus that we'll return to later that were classified by Kreutzer and Skarka. So you see already that this already gives you a good picture of the large set of Calabi Yaus. If you're a bit more careful and you go to non-toric bases, we did this with Yinan Wang, at least at large H21, we can systematically construct all of the bases, full stop, that support elliptic Calabi Yaus. And we get generic elliptic fibrations over those bases that fill things out. We got down to about 150 before it gets complicated. And this gives us some new Hodge numbers for previously unknown Calabi Yaus. Okay, so let me turn to this toric hypersurface construction, which will be the big class that we'll consider. So now we're going to, that's sort of the big picture of how we can systematically describe the elliptic Calabi Yaus, but how do they fit into the known set? So we'll look at this 474 million constructed by Kreutzer and Skarka using the Badarev approach. Basically, a toric variety, just briefly, is characterized by a set of integer vectors in ZD. These are associated with toric divisors. And then you have a fan, which describes all of the codimension 1, 2, etc., algebraic divisors, curves, etc., in the ambient space. The anti-canonical class of a toric variety is given by the sum of the toric divisors, which means that you can never have a compact Calabi Yau described torically because it always has a non-trivial anti-canonical class. But by adjunction, if we take the anti-canonical hypersurface in any toric variety, compact toric variety, we're going to get a Calabi Yau. So we can think of this in the language of polytopes. If we take a set of vertices VI and form a convex hull of that set of points, that gives us a polytope. The dual polytope, given by the set of points in the dual space whose inner product is greater than or equal to -1, if that dual polytope is also a lattice polytope, then the polytope is reflexive. That's also equivalent to the condition that the polytope has only one interior point. And under those conditions, Badarev showed that a hypersurface in that toric variety is generically a smooth Calabi Yau. And so Kreutzer and Skarka constructed, by systematic enumeration, all 473.8 million reflexive 4D polytopes, all of which give rise to various Calabi Yau threefolds. I'll just comment that the polytope nabla and its dual delta describe mirror Calabi Yau threefolds, and the observation that this diagram here is invariant under reflection across what in this picture is a diagonal axis was one of the original pieces of evidence for mirror symmetry. And we'll come back to mirror symmetry at the end of the talk. Okay, so that's the basic idea. Just to illustrate this, let's do a very simple example which connects to the story of elliptic curves. Here's a reflexive 2D polytope. It's P231. We take three rays, the 2, 3 ray, the -1, 0 ray, the 0, -1 ray. That forms a 2D polytope nabla. Its dual is this polytope delta, which is in fact a lattice polytope. This set of points over here now forms the set of monomials in a so-called Tate form for an elliptic curve. So if we then complete the square and the cube, we get the standard short Weierstrass form for an elliptic curve in P231. So this is an example of how a one-dimensional Calabi Yau is realized as an anti-canonical hypersurface in this simple two-dimensional toric variety. And we'll be going back and forth between two-dimensional and four-dimensional reflexive polytopes in the sequel. Okay, so let's go back to the initial question. So I said that there's evidence that most Calabi Yau threefolds have some elliptic structure. Why would that be the case? So there's a theorem proven by Guiso and Wilson that shows that a Calabi Yau threefold X is genus 1 or elliptically fibered if and only if there exists a divisor which satisfies d cubed equals 0 under the triple intersection form, d squared not equal to 0, which really just means that it's not K3 fibered as opposed to elliptic or genus 1 fibered. If d squared equals 0, it means that the canonical class of the fiber is itself 0. And d dot c greater than or equal to 0 for all algebraic curves C, so basically it's got to be in the right cone. So before we start to analyze which Calabi Yaus are elliptic or genus 1, let's just talk about what that means. So let's just, again, kind of a physicist's approach, imagine we have a random triple intersection form. How likely is it that there exists some divisor satisfying d cubed equals 0? Well, there are two possible things that could go wrong with solving that cubic Diophantine equation. The first thing that could go wrong is there could be some number theoretic obstruction. It could be that there's no way to solve that cubic equation over the integers. The second thing that could go wrong is you might have an obstruction in the cone in the sense that you might be able to find a d cubed that vanishes, but it might not satisfy this cone condition. So let's consider each of those possibilities in turn. So let me illustrate the number theoretic type of obstruction. Let's take this simple cubic in 4 variables. This cubic equation has no solution over the integers, and it's pretty easy to see that. Let's imagine x is odd and everything else is even. Then this whole thing is odd, and therefore can't equal to 0. Similarly, if x and y are both odd, you have the same problem. So that means x has to be even. Similarly, y has to be even. But if x and y are even, then z can't be odd, because then this would be congruent to 2 mod 4, so z must be even. But if everything else is even, then w can't be odd, because then it would be congruent to 4 mod 8. And if everything's even, then we can just divide everything by 2 and look for another solution. So that's a proof that we can't have a solution of that equation over the integers. So in 1937, Mordell identified in this spirit a set of homogeneous degree d polynomials in d squared variables where there is such a number theoretic obstruction to a solution. It was conjectured that that's the maximum number of variables with an obstruction. It was proven for d equals 1 and 2. There's a counterexample for quartics. There's a quartic with 17 variables where there's a number theoretic obstruction. In 1983, it was proven by Heath Brown that every non-singular cubic in 10 or more variables has a non-trivial rational 0. And it's proven for a general cubic in greater than or equal to 16 variables. So the general cubic in between 10 and 15 is an open problem. But the upshot is that when H11 gets big, when H11 is bigger than 15 in particular, there's no possible number theoretic obstruction to the existence of a d which satisfies d cubed equals 0. So that's a very rigorous set of arguments. Now, I'll make a slightly more heuristic set of arguments for why there shouldn't be a cone obstruction. This is really kind of a physicist argument. Let's assume that the cone is basically a generalized octant. It's just coefficients all have to be non-negative. And let's look for solutions of a cubic that are in that positive thing. Let's proceed by induction. If we take 2 variables, we have a cubic, and now we can ignore the number theoretic problem because we already dealt with that. So a cubic in 2 variables has at least one real solution. So that one real solution has a 50% chance of being in the right cone. If it doesn't satisfy the cone condition, then we add a variable. We pick the first 2 numbers to be in the cone. We check for the third one, which again has at least one solution. Again, there's a probability of 50% that it's going to be in the proper cone. So this heuristic argument suggests that the probability that you don't have a solution in the proper cone should drop as 2 to the minus h11. So that it should become exponentially less likely. Yes? So now I'm solving the problem over the reals. I'm separating the problem into 2 parts. On the previous slide, I addressed the number theoretic obstructions. Once you've dealt with the number theoretic obstructions, you know that there have to be solutions. So I'm separating the problems. This is not rigorous. This is just giving us a heuristic feel for why we expect that it's going to be hard to have something which is not elliptically fibered as H11 goes up. I'm not claiming especially that the second thing is a proof. This is just a physicist's thing. If we separate the number theory from the continuous part, we look over the reals, what is the probability for a random triple intersection product and a cone structure which is generalized octant that we don't have a solution in that cone? And it goes down roughly as 1 over 2 to the n. It's a bit heuristic, but we'll see this appearing again. Okay, so now let's think about actual Calabi Yaus. So Anderson, Gao, Gray, and Lee have done some very nice analysis of the CCs. They found for threefolds in particular that of the 7,890, 7,837 of them have an obvious elliptic or genus 1 fibration, and there's at least one fibration whenever H11 is bigger or equal to 4. And in general, in fact, these have lots of obvious fibrations. Okay, so they've handled those cases. Now let's talk about these toric hypersurfaces. And this is what Yu-Qian Huang and I have been studying over the last couple of years in a bit of detail. So we've taken 2 approaches. The first approach is to start by constructing a bunch of elliptic fibrations. We choose toric bases because these are built on toric geometry. We expect the base to be toric. We tune Weierstrass models for everything we know how to build in a way that's compatible with the toric structure, and we compare to Kreutzer-Skarka. The other approach is to directly take the Kreutzer-Skarka database and look for fibrations. And I'll describe the results of each of those 2 approaches. So the first approach, we directly construct a bunch of things, by elliptic fibrations, by starting with a toric base and then doing what's called a Tate tuning using that Tate form that I put on the board on the slide of the polytopes, which actually matches perfectly with what you see in the toric geometry. There's a sort of a one-to-one correspondence between a certain class of Tate tunings and the so-called tops of polytopes studied by Kandelis, Perevalov, and others. So basically, we can systematically construct tunings that should correspond to polytopes. I'll just show you how this works starting at the top. The largest value of H21 that is possible is 491 for an elliptic fibration. This comes from the generic elliptic fibration over F12. That's this dot over here. You can't tune anything over that. It's full of these non-Higgsable minus 12 curves and things that force you to have a big gauge group in the F-theory language. Let's blow it up once. Then we get, if we blow it up once at a point, we get, now we're blowing up the base, we get a generic elliptic fibration over F12 blown up at a point, gives us 12,462. Again, there's nothing we can tune. We blow it up a second time, then we have produced an extra minus 1 curve where we can tune an SU2, and then that gives us another elliptic fibration over here, which is now a tuned Weierstrass model over this base. We can blow up again. We get a couple different SU2s on different curves. We can get a product of SU2s. Various other things become possible. This is the full set of known Calabi Yau threefolds with H21 at least 376, and they're all systematically realized by blowing up the base and tuning various Kodaira singularity types at codimension 1. So this is really what Yu-Chen and I have done more systematically. We systematically did this kind of tuning for all Hodge numbers above 240, starting with bases that we thought were appropriate. So the initial sieve gave everything in the Kreutzer-Skarka list in this range except for 18 cases. We checked the remaining 18 cases explicitly, and each of those was in fact elliptically fibered. They had some weird large tunings, some non-flat fibrations, some weird forced Mordell-Weil groups, and it allowed us to identify a new kind of Tate tuning of SU6 with triple index antisymmetric matter, but basically everything fit together there. So the upshot is that tuning Weierstrass models over toric bases reproduces all of the large Hodge number things, all of the large Hodge numbers in the Kreutzer-Skarka database. But at many Hodge numbers, as you go down, there's lots of different polytopes. So this is not really a tractable way of analyzing the whole database. So now let's consider the full database. Okay, so now we're going to take the approach that we have a list of reflexive 4D polytopes. Let's try to understand which ones admit an elliptic fibration. So the first thing we want to do is look for a toric fibration. So basically we're looking for, so Nabla here is a 4D reflexive polytope, and we're looking for a 2D reflexive polytope that is a subpolytope, that is, it passes through the origin of the 4D polytope. There's only 16 reflexive 2D polytopes. They're easy to list, and they've been used in F-theory in a variety of contexts. It's worth noting that we can read off from the -1 structure of curves whether there are sections. Basically, a -1 curve satisfies minus k dot c as 1, which means that it corresponds to a section. So if you have a -1 curve, that's a section. If you have many, you have multiple sections. 3 of them, F1, F2, and F4, do not have -1 curves, and therefore they correspond to genus 1 and not elliptic fibrations. But all of these are at least genus 1 fibers. So now what we want to do is take the whole database of 473.8 million polytopes and look in each one to see whether there's a reflexive 2D subpolytope. Just to briefly give you a sense of how we do this, we make it more efficient by defining the set Sn, which is the set of points in Nabla in this polytope, such that the maximum of the inner product of that with anything in the dual polytope is n, and using the Sn for small n allows us to very easily check for the existence of a fibration. Basically, there's a fibration by a reflexive 2D polytope if and only if one of these 3 conditions holds. This basically says there are 2 things in S1 where their negatives are both in S1. That corresponds to saying that there's a subpolytope that includes these rays. The next one says that you have a subpolytope containing these rays, and the final one says that there's a subpolytope containing these rays, I think. Yeah. There should be a minus sign there. Sorry, that should have a minus sign there. Okay, so we checked all 474 million polytopes. We have a paper out some months ago where we used a simple Mathematica code to do this, and we did everything with H11 or H21 bigger than 140. More recently, we've redone the analysis using Julia, which is a bit faster. If you haven't used Julia, it's a fun language. It compiles just in time, so it's as fast as C, but it's as easy to program as Python. So we've checked all that, and I'll report now on some of those results. Okay, so the upshot is, after checking all 474 million things in the database, that all but 29,000 have a 2D reflexive subfiber. The points in red correspond to the Hodge numbers of the Calabi Yau threefolds for the polytopes which don't have fibers. So there's an interesting structure there. First of all, the largest H21, sorry, there's another typo. That should be the largest H11. The largest H11 is 140. Interestingly, these kind of cluster with H21 equaling around 60 as H11 increases. I have no idea why that is. That's an interesting question. Why are the ones without a manifest elliptic fiber clustering in this way, and what's going on around here? Interesting question. Don't know the answer. We've got the data, and we'll put the data online along with the paper shortly so people can look at it. Let's return to the asymptotics related to this heuristic argument I had that the probability drops is 1 over 2 to the n. For small h11, we can look at the number without a fiber, total number, the percent without a fiber, and these numbers you can see really drop very much as powers of 2, right? 0.6, 0.3, 0.21, 0.11, 0.05. Dropping as powers of 2. So it looks like it's matching what we predicted heuristically, but there's a fat tail. I blew it up here. The gray curve here is the number that you would expect if it dropped as power of 2. This is the fraction dropping as a power of 2, and the number of polytopes goes up quickly. So it's a bit like in the Boltzmann distribution story of fusion in the sun or something, where you have two exponentials competing. Here you've got a bulge here, and the red numbers are the actual numbers. So that's a much fatter tail than the 1 over 2 to the n would suggest, but it still drops off quite quickly. This is a picture of blue here is the total number of polytopes, with this is the index. This is measured in tens of millions. The red ones is the number of polytopes without an elliptic fibration, which peaks at 1,700 here, at a very small number of H11. And the gray is the fraction here, where the dots are the ones with no polytopes, no fibers. So why do we have the fat tail? If it really goes down as 1 over 2 to the n, you would not expect to see this outlier out here at 140, right? This would be suppressed by 2 to the minus 140. That's obviously saying that something funny is going on. So there are two explanations I can think of. One is that we may just be looking at the obvious fibrations, and by a more careful analysis of the Collar divisors, analogous to what the Virginia Tech did for the CCs, we might be able to identify fibrations in those other ones. The other possibility, which I think may be more likely, is that in that heuristic argument, I made the assumption that the Kähler cone was a generalized octant. There's recent evidence by these folks that the Kähler cone, as H11 increases, gets increasingly narrow, even when you include all the different phases of the Calabi Yau. So it's possible that that's what's messing with that 1 over 2 to the n. And that's something we're studying right now with some of the collaborators I mentioned at the beginning. Okay, so where are we now? We've got a nice picture of the 400 million reflexive 4D polytopes, of which 30,000 lack fibers, and the rest have nice 2D reflexive fibers. Does that mean that they are elliptically fibered? So there's a little subtlety there. To be sure that it really means that you have an elliptic fibration, you need to go to the next level of detail and construct a triangulation, which gives an actual toric variety, and make sure that the projection corresponds to a toric morphism to the base as a toric variety. And there's some technical things about the triangulation. It needs to be a so-called fine regular star triangulation. And it was pointed out some years ago by Rosiep that you need to be careful to figure out whether your triangulations actually exist. So let me just run through some of the things that can happen. Some of what I'm going to talk about here is work in progress, but I think the story is very clear. Some of the I's remain to be dotted and T's remain to be crossed, but let's just run through some of the things that can happen. In the simplest cases, all triangulations of the 4D polytope are compatible with toric morphisms onto nice triangulations of the base. A simple example of that is the generic elliptic fibration over P2 has that fiber F10 corresponding to the P231, and the Hodge numbers are 2, 272. There is essentially one triangulation of the 4D polytope, and it reduces to this triangulation of the base. That's all fine. In other cases, there can be triangulations which lead to so-called non-flat fibrations, where an entire divisor is crunched down to a point in the base. Such non-flat fibrations have been studied recently by various people in the F-theory context. Let's take an example. If we take the generic elliptic fibration over F1, this has Hodge numbers 3, 2, 43. In this case, there are two different Calabi Yaus that you can get by different triangulations of the 4D polytope. They project down to two different triangulations of the base. One is this and one is this. This is actually a triangulation of P2 with an extra cone. Remember, this point here is not the origin in 4 dimensions. This is a slice through something that's separated from the 4-dimensional origin. So these are basically, that's a 1D cone. These are various higher dimensional cones. So there's a projection which takes this cone and projects it to the point associated with this cone. So this is actually a non-flat fibration. And these happen all over the place. And that's not something to worry about. It's just something to be aware of. There are more subtle things where the fine regular star triangulation gives rise to a singular base. Singular bases have been considered recently by these folks in F-theory. An example is if we take F3, then we have to get rid of this rays, so to get a toric morphism, the toric morphism is actually onto this singular toric base. Now, in order to get the generic elliptic fibration over F3, which is easy to see from the elliptic fibration point of view, we need to go outside the usual toric construction. So there's a generalization of the usual toric construction that was recently developed by Berglund and Hubsch, in which we consider vex or non-convex polytopes, which can be associated with so-called non-star triangulations of the original polytope. These are still connected to the set of Calabi Yaus by flops, and we just have to generalize our analysis to include these non-star triangulations. It's actually quite clear why we need to do this. The reflexiveness condition in the original Badarev analysis essentially guarantees that the anti-canonical class has no base locus. That is, that if you consider an anti-canonical section, there's nothing it has to contain. But if we consider the generic elliptic fibration over F3, F3 contains a rigid -3 curve. So the part of the elliptic fibration that sits over that is actually a rigid divisor that will appear in every Calabi Yau in that moduli space. And therefore, that will be a rigid divisor that must be included. And so we expect actually to see a rigid codimension 2 object, which is precisely what you get from these vex polytopes. You do like a flip. So you get rid of a codimension 2 thing, you drop down, and it becomes something in the base locus of the anti-canonical class that you have to include. So this actually, I think, resolves this part of the story in a very nice way. Things can get worse. There are some cases in which there's an FRS triangulation which is incompatible with any toric morphism, whether the base is singular or whether it's non-flat. And in some cases, there's no FRS triangulation at all that's compatible with a toric morphism. Here's a simple 3D example which is easily generalized to 4D. This is just a projection. This is a fibration with a P1 fiber, which is vertical out of the board, onto the Del Pezzo 3 surface. The plus ones mean these are out of the board, minus ones are into the board. The star triangulation of this cannot give, there's no star triangulation of this that's compatible with a toric morphism onto the base. But one can prove that, in fact, there's always a fine but non-star triangulation compatible with the toric morphism, which means that there's always some phase of the Calabi Yau that has an elliptic or genus 1 fibration. The algorithm is we just take all the rays of the 4-dimensional polytope that project to vertices of the base. These are always primitive. And then we use those rays to make the 2D, 3D, and 4D cones with the rays. So we use the rays in the fiber to combine with that. That gives us a nice convex polytope, and then we refine it by adding the remaining rays to get a vex polytope. And we always have something then which can be a toric variety where a hypersurface will have an anti-canonical class with some base locus, but which will be a good toric morphism. So as examples, I gave you a case where there was no FRS triangulation. Use this algorithm. This is then the triangulation of the base, and it works out fine. In that other 3D example I gave you, basically we do a couple of flips, and we get a picture that looks like this, where now there's a nice projection onto DP3. Okay, so the upshot of that is there's a nice story by which at least one phase of each Calabi Yau will have a description as an elliptic or genus 1 fibration. How are we doing on time? About 10 minutes? Okay, great. So let me spend the last 10 minutes changing gears somewhat and talking about mirror symmetry and how that fits into this story. So naively, elliptic fibrations and mirror symmetry are not necessarily related. If we have an elliptically fibered Calabi Yau, its mirror is not necessarily elliptically fibered. But it turns out that in a broad class of these situations where we do toric hypersurface constructions, mirror symmetry actually essentially factorizes between the fiber and the base. So let me just walk through that and give you a few little examples. This is kind of a fun story. Another paper with Yu-Chen, a couple upcoming papers with Yu-Chen and Paul that refer to. So basically, here's the idea. If our fiber Nabla2, which is a reflexive polytope living in Nabla2, Nabla4 is a slice, which it always is for a projection. It means that there's a projection on the opposite side from delta to delta 2. But if delta 2 is also a subpolytope, it's also a slice, then we have an elliptic fibration on both sides, and the mirror symmetry factorizes. So there's a huge class of situations where this holds. The simplest case is where we take this sort of simple stacking that I mentioned, where we start with P231, and then we put the whole base over the 2,3 point in the P231. In that case, you just directly construct the mirror, and the mirror is now again elliptically fibered. The base is basically something formed by taking minus 6 times the canonical, it's like 6 times the anti-canonical class considered as a toric diagram. We form a fan over that, and the mirror fiber is again P231. So there's, again, the Kreutzer-Schorka database is full of examples of this. I'll give you an example. Here is P2. This is the toric diagram for P2, and the Hodge numbers of this are 2, 272, and you can use, again, this combination of physics and math to get Batarev has formulae, but we can understand them neatly in the language of physics in terms of the gauge group that lives on this thing. There's no gauge group. We use Tate-Shioda-Wazir to get H11 of the total space. It's H11 of the base plus the rank of the group, which are the things in the Kodaira classes, which is nothing here, plus 1, which is 2, and then we can count H21. The mirror to this is the generic elliptic fibration over this rather horrendous-looking beast, which is given by taking the dual of this with a minus 6. So we take all the toric rays W, satisfying W dot V greater than or equal to minus 6, and we insist that W is primitive. That gives us the set of rays here. The red rays are the minus 12 curves, or the minus 11 or minus 12 actually curves that support E8 factors in the F-theory language or in the Kodaira classification. The blue ones support F4 type Kodaira singularities, and the purple and green are G2 cross SU2 factors. Using that, we can compute the rank of the gauge group, immediately compute that H11 of this new base is, as we need, 272. So this is kind of a remarkably simple way of understanding the mirror symmetry between the 272 guy and its mirror. Another nice example is the self-mirror case where the Hodge numbers are 251, 251. In that case, this is the base. It's again got a bunch of E8, F4, and G2 cross SU2 things. We can figure out the rank. That matches nicely with the H11. And this thing is self-mirror under this same picture. We can do this more generally. We don't have to put all the base on one point or use P231. This also works for tuned tape models that I mentioned at the beginning, where we tune some additional gauge groups. Works for other fibers and bundle structures. Here's another example. If we take F2 as our fiber and we put a base P2 over this thing, that gives us 494 Hodge numbers, and we take the mirror. Now we go through the same kind of analysis. The base is going to be like minus 2K instead of minus 6K. It's a bit simpler, and we can compute the Hodge numbers of the mirror. There's some beautiful stuff about what happens with the mirror symmetry of the fibers, which was discussed in this paper. Let me briefly mention a very beautiful set of examples that we're studying with Paul Ullman, who will be a postdoc here starting this fall. we're looking at an interesting class of cases where both the fiber and the base are reflexive 2D polytopes. So they're generalized Del Pezzos or weak Fano varieties. So in this case, the one that we get if we consider the fiber stacked up over the middle point, which I'll denote by O+, is mirror to the one where we get the mirror fiber stacked up over all points on the mirror base. So as an example, if we take the base to be F16, which is essentially a Del Pezzo 6, a generalized Del Pezzo 6 with 6 minus 2 curves, the fiber is a P2, then the mirror of that is something with a base P2 and a fiber like this, but now the fiber is stacked over all points here, whereas here this base is stacked over, the fiber is stacked over all points on the base here. The fiber lives over the middle point here. And so we can compute the Hodge numbers. This guy has Hodge numbers 835. It's got a Z3 discrete gauge group over DP6. It's easy to see the 8 because it's just 2 plus the 6 blow-up points gives us 8, no gauge group. Here we have 2, and then we have to add 24 for 3 times the rank of SU9 because we tune, and this has an SU9 gauge group over each of the toric rays here. And then there are 4 6 points, meaning that this is, that should be 9 4 6 points. 24, that should be 9, that's a typo. That should be 9 4 6 points, right, Paul? So there's 9 4 6 points, so this is really a Del Pezzo 9. And this is actually all of these, this model and a series that we can build from this where we Higgs the SU9 cubed on a set of 3 bifundamentals to get next SU8 cubed cross U1. This happens if we remove a point from the fiber. We remove another point from the fiber, we go down to SU7 cubed times U1 squared. All of these are really secretly over DP9, so these are really special cases of tuned Weierstrass models associated with the Schern 1919 case. So we can keep Higgsing these all the way down, basically until we get to the Schern. The last one, the SU2 cubed cross U1 to the 7th, is not visible torically, but we can keep Higgsing down and we get the Schern. So there's a nice story there which has a lot of, illuminates how mirror symmetry works for these cases where we have things related to the Schern of elliptic fibrations where both the base and the fiber are weak Fano. Finally, we can generalize this whole story to fourfolds. I didn't mention the story of most Calabi Yau fourfolds being elliptic. I'll just make a comment there. A much smaller fraction of fourfolds are known. Most of the ones that are known are elliptic by the same criteria. We actually know a much larger class of elliptic Calabi Yau fourfolds. If we try to do what we did with Dave Morrison to construct all of the 2D toric bases that support elliptic fibrations, that becomes numerically impossible because there's too many for threefold bases. With Yinan Wang, we did some statistical analyses, and Halverson, Long, and Sung have done some work from Northeastern doing explicit computations. The number of threefold bases that are toric that support elliptic fourfolds seems to be on the order of 10 to the 3,000. So it's a very large number, even of geometries in that case. For many of those, we can again tell this nice story about taking mirror symmetry. Again, we flip the fiber. The base becomes some, for a vertex stacking at least, becomes some multiple of the anti-canonical thing where we produce a fan for that. Simple example, if we take the generic elliptic fibration over P3, the mirror of that is something which has rays in a B tilde, which are the primitive lattice points in a tetrahedron with these vertices, and it's got a gauge group that looks like this. Lots of E8s, F4s, and G2s and SU2s, exponentially many triangulations of that. This particular thing is very interesting because I mentioned this Monte Carlo analysis we did to find all the three-dimensional toric bases that support elliptic fibrations. This thing appears as a common endpoint when you just blow up randomly from P3. You often end up at this point. Okay, I think I've gotten to the end of what I wanted to say, so let me just conclude very briefly. First of all, we have a very clear explicit analysis of all of the 483 toric hypersurface Calabi Yau threefolds, and it looks like all but 29,000 of those have elliptic or genus 1 structure, meaning that in some birational equivalence class they're elliptic or genus 1, and in many cases mirror symmetry factorizes in a nice way between the fiber and the base. So I'll stop there.
Are there any questions?
Excellent talk. Thanks very much. I just had a quick question about the mirror symmetry aspect. So you probably haven't thought about this, but just to ask in case. In the case that both a Calabi Yau threefold and its mirror are fibered, do you have any appreciation for what the number of fibrations on one side might mean on the other, in sort of an enumerative geometry sense?
That's a great question. I haven't really thought about that, but it'd be fun to talk about that. I mean, in particular, you would sort of hope that the mirror would be independent of what fibration you choose. So the mirror, naively, the way that we're talking about this mirror structure, it's going to look a little different if you take two different fibrations. And I'm not sure how, I mean, presumably the resulting things are in the same birational equivalence class. I'm not sure how to see that. One case of that, actually, again, back to this, there's a lot of really beautiful stuff related to the Schern. So from a totally different point of view, looking at non-Higgsable U1 gauge groups that we found with Gabriella Martini some years ago, Daniel Park and Dave Morrison and I did some analysis of these cases where you have non-Higgsable gauge groups over semi-toric bases, so meaning there's one C-star action but not two. And in various cases there, we could actually find sequences of flops that related these things that were essentially the same, but weren't obviously the same. And I think that the same kind of analysis would be needed in your question, where if we take a Calabi Yau, which has two different elliptic fibrations, and we do this mirror construction using both of them. Sorry, I'm thinking out loud. I take it back. I think actually you're going to get, because the toric mirror is the same, if you have two different two different toric fibrations on one side, each of which respects the further condition that it's not only a slice, but there's a projection onto the fiber, then each of them will admit a mirror symmetry, and it will give the same polytope on the other side. So actually there will be two separate, I take back what I said, it will be manifestly the same thing on the other side. So if there's a multiple fibration on one side, both are compatible with mirror symmetry, that will match with a multiple fibration on the other side. Okay. But it would be interesting to study that further. I haven't thought about that.
Thank you.
Great.
There's a question in the back.
Those 29,000, do you know that they don't, or do you not know that they do?
We do not know that they do. This is part of this question that I raised. So all we've done is checked whether these have obvious elliptic fibrations in the sense that we have this subpolytope. There are many ways in which you could have a Collar divisor which would not manifest itself in this way. And so, in fact, Anderson, Gao, Gray, and Lee analyzed their CCs. They found obvious fibrations, and then when they looked, if I'm quoting you wrong, correct me, they looked at the ones that didn't have obvious fibrations. Many of the others had hidden Collar divisors, and I expect the same to be true here. So I think the next thing to do is to look at some of this 29,000 and ask, are they really missing elliptic fibers, or are we just missing them by only looking at the obvious ones? And that's related to the question I asked at the bottom of this slide, which is are we missing them because there are non-toric fibers, analogous to their analysis, in which case we should be able to find them, or are we missing them because they really aren't there and the heuristic argument I gave about the exponential drop is incorrect, and one possible explanation for that is the narrowness of the Kähler cone. And I don't know what the trade-off is between those. I mean, right now I'm guessing that it's some of each, that we're missing a lot of the elliptic fibrations even in those 29,000 cases, but the tail may be a little longer than the 1/2 to the end because the Kähler cone may be narrowing and making it harder to have a solution of the Collar condition in the Kähler cone.
So how many are there for which you know that they do not have a torus fibration?
A small number. All the ones with H11 equals 1, I am confident that there is no elliptic fibration. There are some cases with H11 equals 2 where we can prove there's no elliptic fibration because we can explicitly solve the cubic. The number beyond that is kind of small. That's something we're working on actually right now. But really the only ones where there's an obvious proof that there's no elliptic fibration are with H11 equals 1 and 2.
Are there further questions?
Can you comment on how often you get a zero section of the torus fibration, or only bisection, or can you estimate
Good.
the ratio?
Yeah, good. So we have that data. I said we did two analyses. The one sort of more, the one analysis of the things at larger Hodge numbers, which also include very small Hodge numbers using Mathematica. In that analysis, we kept track of which kinds of fibers there are, whether it's genus 1 or elliptic fibered. At large H11, at large Hodge numbers, almost everything actually has a fibration by the fiber F10, which is the P231, and that's a typical elliptic fibration with only one section. As the Hodge numbers get small, it becomes more common to have just a multi-section or something like that. We didn't do the statistics on which fiber type you have. We could do it, but we just were trying to be really streamlined to get the Julia code to run quickly. So we only have the data here as to which ones are fibered or not. But the rough answer is, at large Hodge numbers, everything's got an F10 fiber. There's one other fiber that appears as you go down pretty frequently, but they both have sections. But at smaller Hodge numbers, you're much more likely to have just a genus 1 fibration. In particular, there's lots of cases at H11 equals 2, and only one of them has a section. It's the 2. Basically, if you think, how can you have an elliptic fibration over P2? You can have one generic elliptic fibration with a section. If you add anything else, I should be a little careful. When you have a multi-section, then you have some whole Tate-Shafarevich group, and the Jacobian fibration of the ones with the multi-section always has a section as well. So these live in groups where many of them just have a multi-section, and then you've got one with a section and a multi-section. So those guys tend to dominate at very small H11.
Any further questions? Well, then let's thank Wadi again.